Hola, buenos días, señoras y señores. Dear ladies and gentlemen, first of all, thank you very much for the invitation to speak here to you, the audience. My name is Thomas Barr from Harris Company, and I would like to show you quite a specific topic of image analysis, that is analysis of SAR data, of radar data, and how we can integrate the workflows that we use in remote sensing for SAR data into GIS systems, of course here ArcGIS. So from Spaceborne imagery to ground monitoring applications. And let me start before I begin with the live presentations, perhaps some words about the company. Harris is a company in the field security and defense, communication and information technology. Quite a large company, US-based, 17,000 employees, and it's the 8th largest company in space and defense in US, with worldwide distributors and offices, customers in almost all the countries in the world. And from the many segments that we have, one is interesting here. That's geospatial systems and services. The one here at the right, represented by the branch Harris Geospatial Systems. That's where I'm from. And we take care about software solutions for Earth observation, cloud-based processing environments, geospatial data acquisition, access and use, custom solutions and training and technical support. And we have an end-to-end chain from data collection, independent from the kind of sensor, from the kind of mode, then transmitting the data, ingesting the data into various systems, software solutions for storing, searching and discover data, and finally for exploiting and disseminate. And this is the part that we will have a look on today. Just very short about our part of our portfolio, about product solutions and our services. The main product or platform I will talk about is ENVI. That's our environment for visualizing images, for do image analysis, an open platform, and integrated in ENVI is SARscape for exploiting SAR data, processing SAR data. We have tools for LiDAR, including our own LiDAR sensors, Geiger mode LiDAR technology. And Imagery, SAR, LiDAR, everything is based upon IDL, the interactive data language. That's a programming language that was used to build all our software solutions. And that means that we can use IDL also to extend, to customize our solutions. Geospatial services framework to bring the analysis into the cloud or an enterprise solution. Jaguar is a platform to disseminate data, to bring the results of our analysis even to areas where we have very low bandwidth. We also sell data and products derived from the data. And finally, an important point is training and consulting. So, in a few words, ENVI, our software platform for processing, analyzing geospatial imagery. It's for all data types, so panchromatic images, RGB, multispectral, hyperspectral, SAR, LiDAR, wide area motion images, full motion video, with data from satellite, from airborne, from unmanned vehicles, with a lot of intuitive workflows to support the immediate data visualization, exploration, and analysis. And as I said, we have it's based on IDL, so we have an API to customize ENVI and create new image analysis tools. And it's fully integrated, as we will see in ArcGIS. The last is also valid for SARscape, our software tools for exploiting SAR images to generate high accuracy products and multiple applications based on SAR data. That gives us simply the possibility to do a monitoring independent from the daylight, to do monitoring day and night with a high revisit days, often revisit time often less than a day. It's a leading commercial off-the-shelf technology, and you can do with it almost everything that can now be done nowadays done with SAR. That includes time series analysis, change detection, surface movement monitoring, radar grammetry, radar interferometry. Of course, important are our partners like Digital Globe, like Airbus, and of course Esri. And we are a platinum partner since approximately 8-9 years. With a common development group in the States from Harris and Esri to integrate both platforms, ArcGIS and ENVI plus SARscape, so that we can do the image exploitation, the image analysis also in ArcGIS. I will show also an example for that. Okay, I think that's enough for the introduction. Let's start with some application examples. I have 3 of those examples. The first one is a time series analysis in an agricultural area. The second one will be flood monitoring, and the third one will be a tool for image registration. So for the first one, we will travel to the Philippines, the island of Mindanao. Here we have Sentinel-1 data, so free SAR data that everybody can download. And we have 10 acquisitions from January 2015 to August 2015. And what I will show live is the complete processing chain from the 10 original images, of course subsetted to save some time, up to the final product, which is a kind of land use map. A scenario is Philippines, the southernmost island, Mindanao, and they're quite in the center. Okay, this is our platform ENVI. Who already of you knows ENVI, has seen ENVI? At least a few, great. It looks a bit like ArcMap. That was also the intention when we built the new interface a couple of years ago. So you have on the left a layer for visualization and organizing raster and vector data. We have a view that can be divided in up to 16 single views, and we have our toolboxes here on the right, a small button bar here. So one important thing is to establish a look and feel that is quite complementary to ArcMap, so that users of both our software and ArcMap don't have to get used to a completely different platform with a different handling. Other things that you will not see here, but that are simply implemented. We read, of course, all data formats from Esri. We can access all the geodatabases in ENVI, all the ArcGIS server structures. We have the same coordinate systems, so you can really drag and drop data from ArcMap into this environment without any transformation. As we implemented the Esri projection engine, we have or can use with internet access the Esri base maps in ENVI, things like that, to make image analysis easy here. And before we see the first Imagery. Here we have our toolboxes, and integrated here you see the SARscape toolboxes with all tools for auto-rectification of SAR images, for interferometry, for time series analysis. And I will use a workflow to process those 10 images, the intensity time series workflow. It contains various steps. I will explain them one by one. It's a complete processing chain, starting with the original data and then doing the processing steps up to the output. And processing, and I have just a standard laptop, but you see processing is fast enough to demo that at a conference like here. So here I have my 10 Sentinel-1 images. Already pre-calculated subsets to save a bit of time. I input a digital elevation model. That's important for the SAR processing. I have one prepared. I could also extract from one via a browser from the internet while I'm doing the processing. And the grid size, the ground resolution for Sentinel-1, that's 15 meters. So I can start with the first process step. It's called multi-looking. Well, we have here interferometric wide swath product. That means we don't see any image in the beginning. We have to extract the information that we can see as an image here within the first processing step. So it's a product that contains much more information than just the SAR images that we need to do our time series of land use. It takes a few seconds as we have 10 images. So it's really time series processing. So now we have the 10 images. They are not geocoded. It looks like geocoded, but it's not geocoded. It's just the subset here in the original SAR geometry. So it's still distorted. One of the challenges we have to face when we work with SAR data. And okay, I can click through here, and let me zoom in a bit again. When I click through this series, you see some typical things. You see small shifts between the images. You see that a lot of things are going on the surface because the grayscale values we see change from image to image. And we see something that often prevents people from using SAR images. We don't see any features. Of course, we can imagine that in the center that might be a river. Otherwise, we don't see any information right now. In comparison to optical images, where you look at an optical image and you see all the features, and then you start, okay, I would like to extract this and that. Here we don't see anything. So we need another processing step. And where is my workflow? Somewhere hidden in the background. There it is. Next step, we have shifts between the images. That's a natural thing. You have the sensor in the orbit traveling with high speed. That means we have often, when we acquire the same area, a shift of a few milliseconds. And that already means a shift of a couple of pixels on the ground. So the first thing to do time series is to co-register all the images, that we really can compare them pixel by pixel with sub-pixel accuracy. Otherwise, it could be that we compare grassland with a forest pixel, or a road with a field, things like that. So a very accurate co-registration is important. So let's do a co-registration. Co-registration is a very complex thing. I just pressed a button. It can be done automatically in the background. It will again take a couple of seconds. And there's a lot of things happening in the background. It's a 3-step automated co-registration. What we know from all the acquisitions is, of course, the information about the orbit. And this orbit information can be used for a first rough shift estimation. That gives us approximately pixel accuracy. Then a cross-correlation between the 10 images is done. Cross-correlation means that comparable features are searched automatically using small windows. And then we can place the images one on the other with sub-pixel accuracy. And in the last and third step, we can refine them, this shift, using so-called coherence images that show the changes from one window to the other window. And that's to achieve accuracy up to 100th of a pixel. Why does this co-registration has to be so accurate? What we should avoid, and therefore we use the best algorithms that can be found, is simply we have to prevent introducing a decorrelation between the 10 images that is induced by the processing. We have enough decorrelation due to vegetation growth and so on in the images. So what we wouldn't like to have here is an additional component derived from the processing. Therefore, the co-registration step is the step that takes most of the time, but it's the most important step. Otherwise, we couldn't do any change detection analysis within a time series. And now when we click through the images, we see we have co-registered them. There are no shifts. If you look at those smaller branches of the river here, no shift visible. So a perfect co-registration. And that's simply a must in our analysis. So again, so what we still see, no features beside the river. So let's do some filtering. And of course, what I show here is not a simple filter like frost or something like that are widely used with SAR images. This is a so-called time series filter. Time series filters have one advantage. They don't work just on one of the 10 images after the other, but also in the third dimension, in the time dimension. And by that, they help us to prevail and to preserve tiny changes in the use of the land, in the change of the land cover, if this is a typical information in our time stack. So filtering in 3 dimensions to pertain all the information that we need. And now we have a completely different appearance. That's now a time series almost looking like grayscale optical images. We see a lot of features. We see a mountain ridge here. We see agricultural area here. When we zoom in, we see here the shape of single fields. It's a rice plantation. We see the changes with the time. That was before filtering. This is after filtering. So now we have a data set that is ready to use for time series analysis. One step is missing, geocoding. And geocoding here in SARscape means geocoding is an auto-rectification process, as we have a digital elevation model as an input. So we get for each pixel the exact position on Earth, derived from the sensor model that we know because of the metadata of our SAR images. Therefore, SAR imagery auto-rectified using a so-called range Doppler approach, that's the most accurate that we have, enables us to gain also base images for image registration. This is the last example I will show. So now we are converting those images from the SAR geometry, and you know SAR is side-looking geometry, so we have a lot of distortions, to really map projection. Again, for all the 10 images. Again, processing done very fast. And now we have a succession of 10 images. Co-registered, filtered, and geocoded. The final step in our workflow is the derivation of multi-temporal features. That's simply statistics on the 10 images. Things like mean, median, standard deviation, gradient, coefficient of variation, and so on for each image pixel are calculated. And we get, in the end, some colorful information. To make interpretation a bit more easier, let me close all those files and open a project that I have pre-calculated, because that enables me to show you the use of this multi-temporal feature extraction with statistics. So, again, what we have is, on the one hand, the time series of our 10 images. From January 2015 to August 2015. And we get this colorful RGB combination of some statistical features. That almost looks like a land use classification. We see the river, we see some of the fields. Here is also a town visible. But how we interpret the colors and what information can we retrieve? For this, I created some regions of interest. You see them here: river, sandbank, urban, stable vegetation, and rice fields. And there's one nice tool. That's time series analyzer raster. So let's start with the river. We see, and let me zoom in a bit, here the river. I have some regions of interest in the river. I select the first one and plot the selected curve. And that's the curve for the river region of interest. You see along the x-axis the timeline, and you see here the values of the 10 acquisitions. It looks like a lot of changes, but look at the backscatter. So the values we see with the SAR sensor, that's a very small range. So water is a very smooth surface. So the radar pulse is reflected off the sensor, and water is mostly black with almost the same values. But what are the red colors here? Let's do a plot. And now we see two things. The range is quite different, with much larger values here. So you see really the river, the first region of interest, there's always river, always water, always the same value, around 0.01. And now we see within the red region, here's really seasonal change. And those are sandbanks, what we see here in red. Very shallow water, sometimes even above the water, and the sandbanks are migrating through the year with the seasons. So we have here water in January, or river in January. Then we have a sandbank here with higher values here in March. Then going down, we see seasonal changes within the river. Next region of interest. We have a lot of green area here. What's the green? Meaning quite high values. That's because of the backscatter of vegetation, very typical values. And we see green means stable throughout the seasons. We have more or less the same values. So much higher backscatter than water, easy to detect vegetation, and always the same throughout the year. So we have stable vegetation, or as we don't have here reference for vegetation, it could be also rough, bare soil. This is something we don't know, but at least it's not an agricultural field, because then we would have seasonal changes. And this we see with the next region of interest. Here I picked out one field. Let me plot it. And that's always fascinating what we can see here. We see the seasonal change within the field, and it's a rice plantation. So we have vegetation cycles from the rice fields that are covered with water. Then the rice plants are set, then they are growing, they are emerging out of the water. They are growing, then finally the rice is ripening, it's drying, and then it's harvested. And in the end we have, again, a field that is covered with water. Those changes mean a lot of changes in the backscattering of the radar pulse. So every stage can be derived from a SAR imagery. And what we see here is a complete vegetation cycle. Here the signature, the rice field, has values. We see that close to water, but more or less shallow water, like we have in the sandbanks that are just shallowly covered with water. So obviously here a rice field is covered by water. Here the rice plants are emerging. They are growing. And this here, this decrease in values, is the ripening of rice, because the moisture in the rice plant changes, and we can visualize this with SAR data. So we exactly know here the ripening of the rice plant starts, and then we go, well, to the here we see the ripening, and then it drops, and what we don't know exactly is where in this range here is the harvesting. And then it's covered with water, a new cycle is beginning. So we can exactly see what's going on in a rice field. And this is used for rice monitoring, especially in Asian countries, to get an idea about the harvest that you can expect. Because it's not like here in Europe, where we have 2 or 3 vegetation cycles always at the same time. No, some fields here are flooded. In some fields, the rice is already ripening. So it's very difficult to do estimations, but we can use SAR data on that. So that's the first example. Now let's go into ArcGIS and have a look at the next example. Next example brings us to Italy, in the Veneto region. A flooding that took place in November 2010. Immediate connection to the torrents in the Cadiz area a week ago here in Spain. So monitoring of flooding with quite high resolution data, 3 meters Cosmos climate strip map, a revisit time of 4 days. 4 days means if you have the same geometry, but just covering the same area, daily revisit time. And I would like to show here the example in ArcGIS. As we talked about the integration of ENVI and SARscape, so the first example, typical SAR workflow in ENVI, and now using SARscape, and now again SARscape technology, but in ArcGIS. Sorry, don't share the same view. Okay. The first thing why also we ENVI users like to work in ArcGIS, ArcGIS is the many background information that we can easily access. So here just indicated with the road net, a Korean land cover, both provided as vector data. In the background, we have some Landsat. We have also a layer of the water bodies. We have here some images. The first here on the left shows where we are with this area here. That's here, south of Padova. There was the major flooding of the river Po here, and that was the village Bovolenta during the flooding. And the task here to make a change detection analysis from SAR data. Let me at first show the images, the two SAR images. This is during the flooding, and this was acquired in the dry state after the flooding. And now we can make a change detection. When we zoom in, we face exactly the same challenges as before. You see the shift between the two images, so we have to co-register them. And also, we have to filter them. Co-registration cannot be done in the same way as that was before, because we have two different sensors, Cosmos Climate 2 and 3, with different geometries. So here we will do at first a filtering and then the geocoding. Again, the two images. And now let's do the filtering. Before and after the filtering. And in the end, we geocode the two images. The one in the dry state and during the flooding, and when we zoom in, now we also see that we have a perfect match between the two images. So again, here not sub-pixel accuracy, but pixel accuracy, which is okay for an operational monitoring. We want to have the results very quickly. And we can do the analysis here in ArcGIS. We have, with the installation of ENVI and ArcGIS on the same machine, here a toolbox with quite a lot of tools. And one of them here is a tool geocoding. So we have a predefined tool for geocoding. That's a script with a Python interface. Now we need a filtering, not one of the standard filters. So I built my own toolbox for the flooding with a filtering script, performing one of the SAR-specific filters from SARscape. I have a script for change detection, and I have a complete workflow in the model builder. But this workflow contains only functionality from ENVI and SARscape. So we see here the processing of the images, the geocoding, the final change detection, and in the end we will have the flood image. So IDL was used to build a script with the ENVI SARscape functionality, and with a small Python interface we can run the script, for example, within the model. And amplitude processing is the filtering using a customized filter script and the geocoding with a geocoded output. And that means all the ENVI and SARscape functionality we have can be brought into ArcGIS. So what we need here, just to do the change detection. The change detection is based on ENVI functionality. We use the before image. We use the after image. And now you see here, starting ENVI process. So now ENVI is running in the background, doing the change detection analysis, which is also not a simple one, but an iterative one with segmentation, several thresholds that are used. And after a few seconds, we have here the flooded area. You see it perfectly matches with what we see here. And now, of course, we have the advantage that we can use all those ArcGIS layers, like the water bodies, to see which areas are flooded, which roads are passable or not passable, where we have to guide any rescue forces, and so on. Okay, last example. Let's go once more back to Envy. Yeah, I just need 5 minutes. Okay, now we are in Rome, Italy. Here's the city of Rome. And what you see are two data sets. The first one is a spot optical image here in a false color visualization. So vegetation is red. And we have a Terracer X strip map. Resolution of the SAR image, 3 meters. Resolution of the spot image, about 12 meters. Now we have said during the co-registration and geocoding process, what we do with SAR data in the processing is very accurate. It's a perfect, rigorous auto-rectification. We know for every pixel the exact location on ground. So we can use properly geocoded auto-rectify SAR images to map our optical images on them, to fuse finally the information both derived from SAR imagery and optical imagery. Well, you can, of course, purchase auto-rectified spot images, for example, or other optical images. Then you have an auto-rectified SAR image and an auto-rectified optical image. If you are lucky, you have really a pixel match. But sometimes, due to different auto-rectification processes and so on, you might have small shifts with a huge impact when you do time series analysis, change detection, and so on. So a way might be to register the optical image on the SAR image. That's something quite difficult. How is this registration done? Well, an analyst looks for tie points. That means points he can identify in the optical images and identify in the SAR images. He looks for some dozens of tie points nicely spread over the overlapping area. Sounds easy, can take hours or be impossible. When we look here at the Vatican City, this is the optical image. We clearly see all the infrastructure, the houses, and so on. This is the SAR images. Completely two different layers of information. And what we see in the SAR images is not the infrastructure houses, but it's reflection of the radar pulse on parts of our buildings, for example. So very difficult to find here tie points that are reliable. And of course, the other thing is we have a shift. The SAR image is geocoded correctly. The optical image has a geoposition in the view, but it's based on some coefficients that are provided by the data provider. So it's not accurate, and we have to remove the shift that can be clearly visible here. And let me go to another area outside. Again, that's the wrong one. Again, we have the shift here. Of course, here we see in the SAR image edges of fields that we can use, but here the tie points to find them is also time consuming. Let's use a workflow for that. Image registration workflow. And that shows, again, like the time series analysis, algorithms might be quite complicated. This is a so-called is an automated registration engine, patented, 3 years to build it. But what we have in the end is a simple user interface. The base image is our SAR. Then we have our spot image. Let's use digital elevation model. The algorithm that we use is one that can handle data from completely different sources as SAR and optical. Let's just use the defaults and press next. Now the action starts to find tie points in the two images, exactly where the image analyst needs a lot of time to find the points, or in the urban area, almost impossible to find them. Here this is done automatically, and while it calculates the tie points, of course, this is something that we can also put into a simple IDL script and run it in ArcGIS. So we get 71 tie points. On the right, we now have the optical image. On the left, the SAR. We see that they are evenly distributed in the overlapping area. And now let's have a look again here, and I use a preview option that calculates the registration of the optical image in real time for this rectangle, and we see that we have a perfect match here. But same is true also in the urban area where it's so difficult to find the points. Statione Termini, the main station, perfect match between optical and SAR. Done in a minute, automated. Very important feature. And doing this in a script in ArcGIS, of course we can do that for a complete stack of images. So something running in the background. And the last slide I have, something like a Outlook. I've showed that on the desktop, but it can be also done as a web service. For this, we have an enterprise architecture called Geospatial Services Framework, fully interoperable with ArcGIS. That means we have our applications built on Envy, SARscape, whatever you need of functionality based on IDL or other languages. We have the Geospatial Services Framework, managing all the various services, be it Envy, IDL, SARscape, and so on, in connection with data store, for example, access of free imagery like Sentinel-1, Sentinel-2. And the middleware system, that could be ArcGIS, ArcGIS server. Communication, HTTP REST, simply via browser commands, Of course, we use the REST definition of Esri, and then the analysis can be brought to the various clients using ArcGIS server, ArcGIS online, so that finally you have the analysis on a tablet, for example. Thank you very much.
Thank you, Tom. Pues, any question? Rápida porque...
Yeah.
No.
How do you choose which image is the image, the base image?
The base image is always the image that is auto-rectified.
Ah, okay.
And then the
doesn't matter if
geocoded
it's
image,
the SAR one or the optical
it's
one.
just to show this here with SAR, but it can be also an optical as a base and another optical or an aerial photo on a map or whatever you need.
Okay, thanks.
Thank you.